Welcome to mini lecture number 8 for Computer Science 252 at the University of Wisconsin-Eau Claire. Today we'll be learning about system calls. This topic is covered in your textbook in chapter 7, sections 1 through 4. And I encourage you to check that out before you go on with this lecture. Or if you prefer, you can do it afterwards. Before we begin, let's ask ourselves some questions. So I encourage you to pause here. What is a shell? What is its relationship to the operating system? What are some of Bash's keyboard shortcuts that can help your productivity? So for instance, what does Control A do? What does Control L do? Control E? What about Control R? How can you autocomplete a file path or a command name? These are definitely worth knowing if you use Bash a lot. And as computer programmers, it's probably likely that you'll use it often. And then the most important question is this. Of all the C functions that you've seen so far, which of these probably go deepest into the computer's operating system? This will be the topic of today's mini lecture. To begin, we'll review some shell commands. You may have seen some of these before, you may not have. We're covering it for the first time really here, except for Control C. So Control C, it will terminate a process that's connected to standard in. So that's the standard way of quitting a program on the command line. The ampersand will run a program in the background. If you do that, the program will run. You can't type anything into it because the standard input stream is disconnected, but it will occasionally output stuff back to you. These other ones deal with processes that are being run in the background or getting them from the background. So we'll talk about some of these in just a sec. Control Z forces the current job into the background. So say you start a program and it's doing the same stuff over and over again. You've accidentally created an infinite loop or a very long infinite loop. So you hit Control Z. That forces the current job into the background. The job is still running. This is a mistake that I made in my introductory C++ course. I thought, hey, I found a better way than Control C, because sometimes Control C didn't work. So instead, I would use Control Z, and I thought that everything was fine. And no, that just meant that the computer was spinning its wheels and doing its computations, and I just didn't realize it. Whoops. So it was still running. I didn't realize that at the time until I logged out or closed the terminal window. Now, if you actually want to quit, kill the process, you can use PS to find out what the process ID is of that job, and then you can use kill, the kill command, to kill that job. We'll talk about that in a moment. So suppose you want to kill a process. Kill is the command to end all commands, literally. So if you want to kill a process, to end it, you can use the command kill and then the process ID of the process that you want to kill. Some systems you can also use the name of the process if it's unique. So that's a nice way of saying, like, hey, please shut down. But if you want to kind of do something more like a force quit, you can do this, kill-9-1. So what this does is it kills all of the processes that you can kill, including the terminal that you're in or any other processes or terminals or applications that you might have running that can be killed with this. So use that carefully. But what's going on here? The 9 here represents the sig-kill signal, and that's a signal that processes can send to each other, and it's basically like a force quit. You can ask a process nicely to quit, and the process might be like, would you like to save your stuff before you quit? Or you can send it the sig-kill signal, and the sig-kill signal says, surprise, this process is done, and it kills the process, and the process doesn't have any say in it. So it's basically said this kill-9-1 is a force quit, and then the -1 means all processes larger than the number -1. Now, since all processes are positive numbers, that means all processes, and some of those processes you won't be able to kill, so it'll just be like, it'll ignore you. And then other processes that you can kill, it'll send the sig-kill signal to all of them. Let's move on now to system calls. Now, system calls are deep level functions that will connect to you and let you request things from the operating system or even directly the kernel of the operating system. Now, with such great power comes great responsibility. You can do things that you really didn't mean to do, and this can cause lots of problems. And there's lots of problems that many other programmers have done over the years. And sometimes you laugh and sometimes you cry. So just be careful, and when you use a system call, make sure that you really know what it's doing, especially when it involves other processes, like forking or killing. You can really screw yourself up and screw your system up in weird ways. Also file, so there's lots of things you can do wrong. Let's just leave it at that. Operating systems, they have two primary jobs, as you know. They manage computer resources and they coordinate the programs that are running on the computer. Now, an operating system isn't just a monolithic program that's running all the other programs. It's usually a collection of other programs. Not just one. There's the operating system, the core, but then there's also a lot of other things that help support that. Other processes, listeners, I/O managers, and other things that might be running. Of these, the kernel is the most important component of an operating system. The kernel is the thing that manages all the hardware on the computer. It has complete control over the computer to do just about anything it wants. It's in charge. And it's always in memory. And usually it's in a protected region of memory to prevent other people from accidentally overwriting it if they have like a Stack Overflow or something like that. So it's in a protected region of memory just for security, right? To make sure you don't screw up the kernel, which then could screw up the rest of your computer irreparably. The system call, applications will make requests of the kernel or the operating system via something called system calls. And again, it's a request. It's not it's a command, but the kernel sees it as more of a request. This request might fail, right? So for instance, when we allocate memory, we request, say, hey, I want an array of 50 integers. Please give me enough memory to hold 50 integers times size of, 50 times size of integer. Give me that many bytes of memory. And the operating system can say, yeah, sure, here you go. Or it could say, no, here's a null pointer. You don't get it. So again, it's a request, and you have to check and make sure whether something actually completed or not. Unfortunately, each kernel and each operating system have their own API for system calls. That means that if you're a pro, you're used to working on the Linux kernel, and then you go to Windows, it's going to be a whole different world. But that's something that you can probably expect. One thing that's really cool is for a while now, we've had this POSIX standard. And the POSIX standard is basically a standard set of system calls that are common to most or all computer systems, all POSIX compliant computer systems. So if you do that, you can only learn this, you only need to worry about learning this set of standard system calls. And then if you really need another one, you could do that. But this allows for portability. It allows you to learn fewer things. You don't have to learn things for different systems. And I like to think that they're pretty elegant too, as far as system calls go. Now, most operating systems, like Linux, organize system calls into families of related calls. We'll see an example of what that looks like in a little bit. First, let's see what a kind of diagram to see what this looks like. Here's a diagram I found off Wikipedia that I think does a really good job of showing how these things are all related to each other. So on the right, the blue boxes represent your program, your application that you're writing. Now, if it's POSIX compatible, that means that it uses POSIX approved functions. So either it will be talking to the GNU C library, or it'll be talking directly to the kernel here via system calls. Now, not all system calls or functions are going to be POSIX compatible. You could have other ones too. So Linux is going to provide some other ones. A lot of Linux commands are POSIX compatible, but not all of them. And so if you use ones that aren't POSIX compatible, well then, but Linux specific, then you're Linux specific and not POSIX compatible. Same for any other operating system. So the green region here represents the GNU C library. That represents a whole set of commands and functions and stuff that you can access just in built-in standard GNU C. It's going to cover a lot of space, but it's not going to be all of them. Some commands that you want to do are going to talk directly to the kernel rather than going through the C library. Those are called system calls. Let's see some example system calls. Remember how earlier I said that they're grouped into families in most operating systems. So let's look at what some of those families are. One family is file management. So this has routines such as, and wait, before I say, I want you to pause. See if you can remember some of the file I/O routines. Now here are 4 examples. These are some of the most low-level file management routines that you can have. There are other ones like, say, fprintf, which I wouldn't call really a system call. It's something that would be a function call that's calling the C library, and then somewhere under there, it's under the hood calling one of these. But by itself, it's not really a system call. It's a function that calls a bunch of other stuff, formatting and whatnot, and then somewhere under the hood, there's a low-level kernel call that might get called. So that's the file management, some of them. Other ones include device management. So attaching or detaching devices. So when you plug in a USB, for instance, does that do something? Attaching or mounting or unmounting, say, a file system or like a hard drive, for instance. Device I/O, setting device attributes, all that stuff is there. So what version of mouse driver do I have? Stuff like that could be device management. Communication, so creating and deleting communication connections like a socket, sending or receiving data to other processors, to other CPUs, to other processors on the same computer, perhaps, which we'll talk about later, not this lecture, but another one soon to come. And then attaching or detaching remote devices. Another set of system calls, another family, is protection. So getting and setting file permissions. That's something that's a low-level thing. You don't want just any program to be able to just say, hey, I'm going to set this file permission to anything. You want that to be a protected thing, so it has to go through the kernel. And then finally, process control, and this will be the topic of the next mini lecture. Process control involves being able to control this process, being able to control other processes, being able to spawn processes, being able to kill processes. It's really cool, and we'll talk about that more in a bit. If you want to know more, I encourage you to check out some of these. The first bullet point here has a really good overview of system calls and error handling, and I really encourage you to check that out. If you look at one of those, look at that one, but please do check that out. Take 5-10 minutes. You can get through with it in 15 minutes, no problem. If you want to know a little bit more about what system calls look like, there's some good tables and references here. I encourage you to check out the second one for that. If you really are loving this and you really like assembly in C, you can also try the last one. It's also good for just kind of browsing at and seeing like, how deep does this rabbit hole go? I don't encourage you to go down that rabbit hole unless you really like it. Then by all means go for it. But it's a little more low level than I intend to cover here. But it's interesting and just interesting to look at and see, oh, this is a little bit of what's going on. Not all of your education is being able to do everything. Sometimes it's gaining an awareness of what's going on around you, so that when someone asks you about something, you can, you know a little bit about what's going on. Here are some review questions. So if I type a command followed by ampersand, what does that do? If you use Control-C or Control-Z to stop a program, did it really stop? Is it in the background? If it's not stopped, how do you revive it? Or is it revived? Is it paused? Is it not paused? What do those things mean? What is a system call, and what are system calls' relationships to the C library, the kernel or operating system, and to the program that you write? What are some examples of system calls? What families do they live in? So those are some review questions that I encourage you to think about, pause and reflect a little bit, and then I'll go on to a practice problem. Practice problem number 1. If you haven't already done so, try writing a program that does simple file input and output using C. Try getting it to write text, ASCII text. Try getting it to write binary. Challenge yourself. If you want, here are some ideas. So first, write a program to initialize an array of values, maybe from standard in, maybe randomized, from the random library, maybe ordered, all in order, maybe like sorted, maybe not, and output the results of that array to a file. Maybe you could even write a routine that would take an array of arbitrary size and write it to a file. I've done that in Fortran. I've used it so many times in all of my code. It's one of the most valuable pieces of code I've ever done. So make like a little library of input and output array functions. Another one is to write a program to read in that array and then print the results to standard out. So again, you could write some routines like a function or two that will say you give it this file name and you give it an array in the array size, and it will output that array to a file. Brilliant, useful program, and or brilliant code, and you can use it again and again. It could be your own .c and .h file. Wink, wink, nudge, nudge. Another challenge is to try to use the system call to execute another program. This is something we'll be doing in a little bit, but if you want to try getting a little ahead, this is a great place to start. So that's it. Thank you for your time, and I hope that you have a great rest of your day. Bye.